This lesson is going to start transitioning us from thinking just about how atoms are connected and where the valence electrons are located into starting to think more about what molecules actually look like in 3 dimensions. I've mentioned a few times that Lewis structures are just to show connectivity. They do not represent an actual 3-dimensional structure, that the way we draw a Lewis structure in terms of like the angles between the bonds and stuff is not meant to convey the real way the atoms are arranged in 3-dimensional space, just how they're connected. So the first thing we need in our toolkit to understand the shape of molecules in 3 dimensions is what's known as the hybrid orbital model. So the hybrid orbital model is a model of bonding in molecules that accounts for the shapes that we actually see. So if we think about what we know about atomic orbitals, we have s orbitals, we have p orbitals, we have d orbitals, we have f orbitals. Most of covalent bonding is done via s and p orbitals, things that have their valence electrons in s and p subshells. And if we think about how those things are oriented, particularly the p orbitals are the highest energy electrons for a lot of the things that are doing covalent bonding. We have p orbitals oriented along like the y-axis, the x-axis, and the z-axis pointing towards you, which I'm not going to try to draw. So if the atomic orbitals as they are responsible for a lot of bonding, we would expect to see a lot of 90-degree angles in molecules, and the fact is that we don't. So the atomic orbitals as they exist must not be what's responsible for bonding. So the hybrid orbital model essentially takes atomic orbitals and does what's called a linear combination to them, which is different combinations of adding and subtracting is kind of the simplest way to think about it. The functions, remember that orbitals are described by mathematical functions, and what we get is hybrid orbitals. So hybrid orbitals are the result of different combinations of atomic orbitals. So if we, for instance, take an s orbital and we combine it with a p orbital, the way that the linear combination mathematical process works is that if you put 2 things in, you get 2 things out. So if we put in an s and a p, we're going to get out 2 different hybrid orbitals, both of which are known as sp orbitals, and they look pretty much like a lopsided p orbital. So they have a big end and a little end, and they point in opposite directions. So these would be known as sp orbitals. If we take an s orbital and we combine it with 2 different p's, we get 3 things out since we put 3 things in. The shape is fundamentally the same as sp orbitals. All of the hybrid orbitals have the same sort of lopsided p look. The like degree of lopsidedness varies, but that's not important. And what we find is that they point to the corners of a triangle. So if one points straight up, we would have one that points kind of down and left, and one that points kind of down and right. And we name these sp2 orbitals. So on and so forth. I'm not going to do out examples for all of them, but this is the general idea behind hybrid orbital theory, is that we're combining atomic orbitals, and what we get is these things known as hybrid orbitals that more closely align to the actual structures of what we see. So for instance, the sp orbitals, the orientation of these is 180 degrees apart. It is generally the bigger lobe of these that is actually involved in the bond. So if a central atom were, or if a nucleus was at the center of this orbital, these two orbitals on the same atom, so let's say that blue is our nucleus. If we put these two orbitals on the same atom, we would have one pointing out this way, the big side, and the little side goes this way. And then we would have the other one goes this way with its little side over here. So there is 180-degree angle in between these two hybrid orbitals, and 180 degrees is an angle we actually see in molecules. In this angle, they're pointing to the corners of a triangle. It's 120 degrees in between the orbitals the way they are oriented. 120 is, again, an angle that we actually observe when we look at molecules. So these hybrid orbitals are a pretty good reflection of of the actual structure of molecules. So a little disclaimer on this is that the hybrid orbital model is very much a model. Actual bonding in molecules is governed by what's known as molecular orbital theory, which is more complicated, and usually more complicated than you need to figure things out. So the hybrid orbital model is useful because it is relatively simple to look at something and go, sp2 hybrid, I know what that's going to look like. And we'll see how we can do that as we go through this video. But actual bonding in molecules gets a little bit more complicated in terms of how molecular orbitals are generated, but that is a topic for another course. So what you need to be able to do is understand when you look at a Lewis structure based on how the electrons are arranged around the central atom, what the hybridization of that central atom is going to be, and that's going to help us understand the shape of the molecule as it actually exists. So what the hybridization is, so the hybridization of an atom is determined by how many what we call electron domains are on that atom. And an electron domain is just, an area where there are electrons. So one lone pair is one electron domain. So if an atom has 3 lone pairs on it, that's 3 electron domains. And any bond is 1 electron domain. Single, double, or triple bonds is 1 electron domain. So a single bond is 1, a double bond is 1, a triple bond is 1 electron domain. So when we're counting how many electron domains are around a central atom, it's usually the central atom that we care about, the hybridization. You're essentially counting how many lone pairs are on the central atom and how many peripheral atoms is it connected to, is usually how I like to think about it. So depending on the number of electron domains, we have different names for the hybridization. So we saw sort of the first two. Essentially, we need an orbital for every electron domain. If there are 2 electron domains, we need 2 orbitals, so we need to combine an s with a p, and that gets us sp. If there are 3 electron domains, we need 3 orbitals, so we need to combine an s plus a p plus another p, and we call those sp2. So the 2 is referencing that there were 2 p's in this combination, as well as an s, that got us the hybridization. As we go on, 4 electron domains, we need 4 orbitals, so we put in a third p, so we call those sp3. Now at this point, note that we would be out of p orbitals. There are 3 p orbitals in a p subshell. So as we move on to 5 electron domains, we have sp3, and then we need to bring in a d orbital for our next kind of level of hybridization here. So we call these sp3d, and 6 electron domains is the highest you will encounter in this course, and we call those sp3d2. So we can use this idea of electron domains to identify the hybridization, and again, this is going to be useful going forward in determining the shapes of molecules. So let's look at some examples. So we are going to identify the hybridization of the central atom in each molecule below. So why don't you pause here and give this a try based on what we've talked about so far. So looking at each of these is just stuff on the central atom that we are interested in. So we don't need to worry about lone pairs on other atoms or anything else. It is just the central atom. So first off, let's make sure we're thinking about the right atoms here. So highlighted in yellow is the central atom for each of these molecules. So we're looking for what is connected to that. How many lone pairs does it have? How many peripheral atoms is it connected to? So in our first example here, we have carbon connected to a hydrogen, another hydrogen, and an oxygen. Remember that that double bond still only counts as 1 electron domain. So this has 3 electron domains. So we call that sp2 hybridized. In the next one, our xenon is connected to a fluorine and another fluorine, and it has 1, 2, 3 lone pairs. So that gives it a total of 5 electron domains, which we call sp3d. Next up, in the top right, we have ammonia connected to 1, 2, 3 peripheral atoms, plus it has a lone pair. So that is 4 electron domains, which we call sp3. Carbon dioxide is bonded to 2 peripheral atoms, and it has no lone pairs. So that is 2 electron domains, which we call sp hybridized. And then last but not least, xenon is connected to 4 peripheral atoms, plus it has 2 lone pairs, for a grand total of 6 electron domains, which we call sp3d2.